My name is Dane Quinn from the University of Akron, and today's video lecture will be concerned with projectile motion. Projectile motion describes the motion of a particle or a point mass as it moves through space, subject only to the force due to gravity. So here we have a particle, which we'll label as B, that follows this trajectory given by a dashed line. So at the initial time, maybe it's here, and we have an initial velocity, which we'll describe as v of b at time 0. And in addition, if we identify an origin, O, say here, then we have the initial position of this ball as rb with respect to O, again at time 0. So again, given these initial conditions, the ball follows this trajectory and then, maybe hits the surface here at the end point. Now, for these projectile motion problems, this dashed line, which is known as the trajectory, only depends on the initial conditions. So in particular, the initial position, as given by this vector rb with respect to O, and the initial velocity given by vb, again at time 0. So if I know these quantities, then I can find the resulting path through space. Now, here we would like to develop the equations of motion properly by applying linear momentum balance, and then go and solve those equations to determine the dynamics of the system. The motion in the horizontal and the vertical direction, for example, and the trajectory, the path through space. So in order to do that, let's go and identify the forces that act on this particle. Again, as we've said, projectile motion describes the motion only subject to the force due to gravity. So when we consider projectile motion, the only force acting on this particle arises from gravity, or the gravitational load. We are neglecting things like air drag, any sort of wind effects, that kind of thing, and we're only looking again at the force due to gravity acting on this particle. Now, we also assume that the motion lies in the plane, so that the trajectory is solely contained in the plane of the paper or the computer screen or whatever you're viewing this on. Now, we need to describe ultimately the kinematics of this system. So we need to determine coordinates and directions that will allow us to determine the configuration of this ball. So again, with an origin defined here, we can identify directions I and j to be horizontal and vertical, so that the position of this ball, which is again described by r of b with respect to O, can be measured in terms of Cartesian coordinates, namely the displacement of the ball in the horizontal direction, which we'll define as x, and then the displacement of the ball in the vertical direction, which we define as y. So x and y are coordinates that will determine the position of B with respect to the origin O. Expressing that position vector in terms of the coordinates, we find that the position of B with respect to O, again, this is a function of time because the ball moves through space, and the position vector changes, can be written as x of t in the I direction plus y of t in the j direction. Here we're able to relate the measurements that we make, the coordinates, to the position vector in terms of the directions that we've defined, namely I and j. With those coordinates, we can find the acceleration. Just taking the second derivative of position, the acceleration can be written as, and again this is a function of time, x double dot in the I direction plus y double dot in the j direction. At this point in the process, I have not determined x double dot or y double dot. I'm merely relating those measurements and their second derivatives to the acceleration. Also, looking at the kinetics of the problem, we can construct a free body diagram. Again, the only force is due to gravity, and in terms of the directions that we defined and the parameters of the system, that force is minus mg in the j direction. So here we are specifying the force as a vector on the free body diagram. Now we apply momentum balance. So linear momentum balance, as applied to this particle, gives the following. Sum of the forces equals mass times acceleration of the ball, and the mass times acceleration is m x double dot in the I direction plus y double dot in the j direction, while the forces, the total force, only arises from this force due to gravity. Right? So that's minus mg in the j direction. We can rewrite this equation by taking the left-hand side and moving it over to the right-hand side and collecting components. So 0 now becomes in the I direction. Notice that I have nothing over here, and I just have mx double dot. And in the j direction, I have my double dot. And then when I take the force and move it over to the right-hand side, we have plus mg in the j direction. So now this is a vector equation. It has two components, one in the I direction, one in the j direction. But the only way that the right-hand side can be equal to 0 is that if both of these components vanish independently. So the component in the I direction must be equal to 0, and the component in the j direction must be equal to 0, which gives us two scalar equations. Or taking components in the I and j direction, we find that mx double dot equals 0, while in the j direction, my double dot plus mg equals 0. Well, we can simplify these equations, and notice here that the mass can be cancelled out from all of these terms to find the following equations of motion. X double dot equals 0, and y double dot equals minus g. And these two equations describe the dynamics of this system. So note that we've come up with equations for the motion in the horizontal direction here, and the vertical direction below. Really, these equations amount to constant acceleration for this problem. In order to find the dynamics, we must now solve these equations. We have the acceleration, so we must integrate to find velocity. Again, the acceleration comes from the equations of motion, linear momentum balance, and then we'll integrate once. So in the horizontal direction, we have x double dot And I'm going to use tau as my dummy variable in the integration. Right? So I'll take x double dot equals 0, and I'll integrate it from 0 to t. The initial position to some position along the trajectory. And again, here tau is a dummy variable. Likewise, I will do the same for the horizontal component. Y double dot equals minus g, and we'll integrate that with respect to time from 0 to t. This sort of notation, where I have an operation outside of the equation in brackets, just implies that whatever I do to the left-hand side, so here I'll integrate the left-hand side from 0 to t, I will do the same thing to the right-hand side. So I'll integrate the right-hand side from 0 to t. Now, integrating this, the left-hand side is the integral of a derivative. In particular, x double dot is the second derivative of x, or it's the derivative of dx dt. So when I integrate the derivative of dx dt, I simply get dx dt evaluated at the limits of integration. So the left-hand side becomes x dot at time t minus x dot times 0 equals 0. Or x dot is equal to vx, where we've defined x dot at time 0 to be equal to vx. So vx is the initial speed of the particle in the horizontal direction. Doing the same thing for y, we find that y dot at time t minus y dot at time 0 is equal to minus g times t. We integrate minus g from 0 to t, and we get this. Or solving for y dot, minus g times t plus vy, where, as before, y dot initially is defined as vy. So by taking the acceleration and integrating, we can find velocity. Well, we'll do this again to find position. We go from acceleration, we integrate to find velocity. We take the velocity and we integrate to find the position. So again, using tau as a dummy variable, x dot of tau from this expression is equal to vx. Integrate from 0 to t. And y dot of tau is minus g times tau plus vy. Integrated from 0 to t. So once again, we will integrate the left and the right hand sides to find that x of t minus x0 is equal to vx times t, or solving for the horizontal component, vxt plus x naught, where here x times 0 is equal to x naught. So x naught is defined as the initial displacement of the particle in the horizontal direction. The same for the vertical component, y of t minus y0 is minus g over 2 t squared plus vy times t. Or, finally, solving for the vertical component, minus g over 2 t squared plus vy times t plus y naught. And you can probably guess that the initial displacement in the j direction is defined as y naught. So now we have the position y and x as a function of time, and the velocity y dot and x dot both as a function of time. So given the acceleration, we integrated to find the velocity, we integrated again to find the position, and now we have the dynamics. We have the motion of a particle. And these solutions are valid for any particle undergoing projectile motion. And remember, projectile motion was motion subject only to the force from gravity. Well, let's look at these responses in a little more detail. Here we have the horizontal and the vertical displacement of the ball as a function of time. But if we're interested in the trajectory in space, we'd really like to know the path through space, perhaps y as a function of x. So we can do that. Here I have shown the horizontal motion and the vertical motion as a function of time. Right? So in particular, this is y versus t. In this panel, I've drawn the horizontal displacement along this direction, and then I've drawn time in this direction. And notice that time equals 0 is here, and as time increases, we move down in this panel. This will be useful because I'm going to take these two results and construct a parametric plot here of horizontal versus vertical displacement. So now I'm going to assume that the particle starts at the origin. So we're measuring from where the particle begins. In this panel, we'll show the horizontal motion. So x of t is equal to vx times t from our solutions. So notice that x simply increases linearly in time. And perhaps we have some final time here. And so at t final, we have some horizontal displacement x final. Now I can look at the vertical motion in the same way. So this is y as a function of time. From the solutions, y of t was equal to minus g over 2 t squared plus vy times t. So we end up with a representative plot as shown in green. And this is parabolic because the motion has a term that looks like t squared. And here, again, let's assume that the final time is there, and then we might have a final displacement of the particle given by this height. Notice that this final time in the x versus t plot must be the same as this final time in the y versus t plot. Now, if I would like to construct a plot of the trajectory, what I can do is take, for example, the horizontal motion at the final time, and I can pull that all the way up to this plot for the trajectory. Likewise, I can take the vertical motion and I can move that across. And so at the final instance, t final, the particle must be here at this point, which corresponds to x final and y final. Right, so basically at the final time, we can move x into this plot, and at the final time, we can move y into this plot. Well, let's do this again for some other point. Let's maybe pick the maximum point. So I will take some intermediate time, right, at which the maximum occurs, and I will move that over into the trajectory. Likewise, I'll take the same time in the x versus t plot, and I'll move that into this spatial plot. And so at this point in time, the ball must be here. Okay, let's do it again. All right, let's take some intermediate early time, maybe here, and move that across. And do the same in the horizontal direction. Okay, so maybe at this time, and find a third point. So I could continue to do this process by taking a single value of time and looking at the y component, and at the same value of time looking at the x component, and ultimately I would have constructed the trajectory. So in blue, we're able to find the path through space, x versus y. Now, using the equations for the response of the projectile, I can actually obtain this curve. So here I will take the horizontal displacement and use that to solve for the time. In particular, t is equal to x divided by vx, just solving this equation for t. And then from there, I'll take that and I'll introduce it into my expression for y, which gives me y of x equals minus g over 2 times t squared. Well, t is x divided by vx plus vy times t, and again, x divided by vx. So I am able to solve for the vertical displacement as a function of the horizontal displacement. And again, this curve is parabolic in x because there is a factor of x squared. It starts at the origin, right, because we assumed that x0 and y0 are equal to 0. And in this case, the projectile would follow this trajectory. So given these equations for the time response, we're able to find the trajectory of the problem where time parameterizes this curve. To this point, we have described the initial velocity in terms of components in the I and j direction. Right, so we said that Vb at time 0 was Vx in the I direction plus Vy in the j direction. So again, looking at the ball at some initial time, right, we had Vb at time 0, and we measured the component in the I direction and the component in the j direction. But that's not the only way that we can describe velocity. We could, for example, describe the initial velocity in terms of the initial speed, which is v0, and perhaps an angle of inclination theta. Here we have the initial velocity given in terms of speed and direction. So now, in terms of those quantities, we can write the initial velocity as v0 in the appropriate direction, which for an angle theta reduces to cosine of theta in the I direction plus sine of theta in the j direction. So again, magnitude and direction of the initial velocity. This expression, in terms of components in the I and the j direction, must be the same as this expression in terms of magnitude and direction, because both of these expressions represent the initial velocity, which is the same vector. So as a result, we can compare components in the I direction and components in the j direction to show that x dot at time 0, which was defined as Vx, must be equal to v0 cosine of theta. And likewise, y dot at time 0, which again was defined as Vy, is v0 sine of theta. and we're able to relate the Cartesian measurements, Vx and Vy, with magnitude and direction of the initial velocity. So now, in terms of V naught and theta, we can solve for the motion once again. X dot is Vx, which happens to be in this case V naught cosine of theta, and x of t becomes V naught cosine theta times t. Doing the same for y, we find that y dot is minus g times t plus V naught sine, and y of t is minus g over 2 t squared plus V naught sine of theta times t. And of course, both of these assume that x naught and y naught are equal to 0. If the initial position of the particle is not at the origin, right, then we'll have some additional contributions to the position measurements from that initial displacement. And then finally, the trajectory, y of x, in terms of these expressions, let's recall what that was, gx squared divided by 2 vx squared plus vy times x divided by vx can be written as minus gx squared divided by 2 v naught squared cosine squared plus tangent x. So here we've written the trajectory in terms of the Cartesian measurements, Vx and Vy, and the magnitude and direction of the initial velocity, V naught and theta. Initially we said, of course, that the trajectory and the dynamics of the system are completely defined in terms of the initial conditions. So if I know the initial conditions, I can determine what happens in future. But oftentimes we like to define the trajectory in terms of auxiliary conditions. So perhaps conditions that must be met in the future. These auxiliary conditions will provide equations that can be solved to determine the initial conditions. So again, if I knew the initial conditions, I could completely determine the trajectory. But if I have some conditions that I would like to meet, for example, in terms of a secondary position, so I'd like the ball to pass through some point, then that requirement will give me an equation that I can use to solve for the initial conditions that lead to the appropriate trajectory. So again, the first one we'll look at are in terms of a secondary position. Right, so assume that the trajectory passes through some point xs, ys at some time ts. So here again the particle starts at some initial position x naught, y naught, and then at some future time we would like for the particle to move through a secondary point, which is given by xs ys. And here the question would be, what are the initial conditions that are required to make this happen, right? What's the initial velocity, for example, needed so that the particle passes through this point? Well, we'll essentially look at the equations for the trajectory. We need the position of the particle at the final time ts to be equal to xs and ys. So x of ts must be equal to xs. Well, going back to the equations for the motion, x of ts is vx times ts plus x naught. So this came from our solution to the dynamics. And this is our auxiliary condition. Looking at y, we find that y of ts is ys, and again from the equations of motion and the resulting solution, minus g over 2 times ts plus vy times ts, and then plus y naught. So the trajectory must satisfy our auxiliary conditions, and it must follow the motion that we predict from linear momentum balance. So this gives us two additional equations in terms of the auxiliary position and perhaps the unknown time. Notice that we can combine these into an equation for the trajectory. So we can say, for example, that y of s is minus g over 2 times ts. Well, ts here can be solved as xs minus x naught divided by vx, and that's squared, plus vy times xs minus x naught divided by vx, again, ts is equal to that quantity, plus y naught. This gives us a single equation where we have removed the time ts to relate the desired final position, namely xs and ys, to the initial conditions, x naught, y naught, vx, and vy. So we might be able to use this equation to solve, for example, for the unknown initial velocity required to pass through this point. So again, if we have a secondary position, we can use that information to develop another equation that will allow us to determine the appropriate initial conditions. Because I can't specify all the initial conditions and the secondary positions independently, right? Those two things have to be consistent with one another. Another auxiliary condition that we can look at is the maximum height. So let's assume that the maximum height is given as y equals y star. Perhaps there's a ceiling here that we just want to come up and graze before coming back down. And this might occur at some unknown time, t equals t star. So again, y star is the maximum height. And that maximum height occurs at time t star. And here I'm going to assume that x naught is equal to 0 and y naught is equal to 0. So we're starting at the origin. As a result, the condition for reaching the maximum height is that the velocity at this point must vanish. So notice that y dot at this time equals 0. Well, the velocity from the dynamics is given as minus g times t, and again here we're looking at t equals a specific time t star, plus vy. So I can use this equation to find the time at which the maximum height occurs. And solving, we get t star is vy divided by g. So again, this is the time at which the maximum height occurs. And then I can introduce that into the position to find both the horizontal and vertical displacements of the ball at that time. In particular, the vertical displacement at this time was equal to y star, and we can solve that minus g over 2 times t star, so that's vy divided by g squared, plus vy times t star equals vy squared divided by 2g. So this becomes the maximum height in terms of the velocity in the j direction. In terms of the magnitude and direction of the initial velocity, this becomes v naught squared cosine theta squared divided by 2g. And then, likewise, we can find the horizontal displacement. So x at t star is equal to vx times t star, and here that becomes vx vy over g, because again t star is vy over g, or in terms of the speed and inclination of the initial velocity, v naught squared sine theta cosine theta divided by 2g. So if we have information about the maximum height, we can use that to find the initial speed in the j direction. And we can also find the horizontal displacement of the ball at that point. Again, these are auxiliary conditions so that we know something about the future behavior of the particle after it is released. And we can use that information to find the right initial conditions that give rise to the desired motion. So this is our lecture on projectile motion. We've gone through, we've derived the equations of motion. We have solved those equations of motion. And then we've talked a little bit about, again, auxiliary conditions, secondary position, and maximum height, in particular for these examples. So that's it. Thank you very much, and we will have additional examples in other video lectures.